Okay, let's start. So our current topic is pumps, all right, but this is also closely related to what we just did, which is pipe flow, because normally the pipe flow, there's a pump there, all right, normally, all right, so far, the last few lectures, we looked at this equation, all right, and we'll be focusing mainly on this one, the losses, all right, losses due to major losses and minor losses, all right, major losses in pipe, minor losses in fittings, accessory, entry, exit, valve, from small pipe going to big pipe going to small pipe, and so on, all right, and we also touched a little bit on what yesterday when the pipes are in parallel, all right. In series, is just one pipe going to another. Parallel, your flow branches out. We'll do more tutorial problems on that, and also we'll also explore that series and parallel when it comes to pumps, so that you get a better understanding of what's going on. Okay. So and also so far we know that power. All right. This is the power to the fluid. Is equal to m dot GH. All right, pump. Okay. So basically, this equation is per unit m dot R. All right. This energy equation is energy per unit mass flow rate per unit gravity. All right. So to get back any pressure, power, or whatever, you have to multiply m dot G. All right. So okay. So where should I go from here? I can do two things. Sure. I guess I can talk about the pump. Maybe I talk. All right. So that the pump is just a general name. All right. It can actually be can also call it a fan, a compressor. All right, or a pump. Okay, it's known by many names. All right. And what's different, all right, that we'll talk about a little bit about the different type of pump, all right, because if you look at the power, let's say the power pump rated 5 kilowatts, all right, so rated at, all right, so first thing, there's two power, all right, normally the pump has the shaft work going in, and then somehow the pump power to fluid, which is normally equal to m dot GH. The conversion normally not 100%, all right? Some get lost in noise, vibration, and other things, all right? So the shaft work is normally omega times torque, is it? That's power. Correct. Yeah. Okay, this one m dot GH. So the pump efficiency is normally m dot GH over omega, the torque driving the pump. All right, for shaft work going in. All right, and that's normally less than 100%. Okay, unlikely you get 100%. All right, 80-90%. Okay, that side. So normally the rated power, normally they rated on this side. They rate this one, omega T is 5 kilowatt. Right? Hopefully most of that goes there. Okay, so let's say the shaft work for this particular pump, they rated 5 kilowatt or some other number. That 5 kilowatt can go towards, all right, there's two, well, G doesn't change much. Okay, you can have for 5 kilowatt, so 5 kilowatts is equal to m dot GH. You can have a high m dot and a low h, or you can have moderate, or you can have the opposite, low m dot and high h. What that means is, all right, you can either move a lot of fluid, but give to a high m dot, but give each unit of fluid only a little bit of energy. All right, or you can move a little bit of fluid and give each unit of fluid a lot of energy. Does that make sense? Two types. All right. So that's how, and the pump that does the first and the other one, or the moderate, all right, to operate efficiently, then the design is different lah. Okay, if you want to move a lot of fluid, let's see that, and just give it a little bit of energy, all right, that energy goes into well, let's draw the pump lah. Okay, so all right, so based on this equation, if I leave the pump here and I move everything to the other side, okay, this is how it will look like. Head loss is equal to P2 minus P1 over rho G, final minus initial, plus V2 squared minus V1 squared over 2G, plus H2 minus H1, plus head loss, plus head turbine. Okay, so in this case, what is the height difference? No, okay, so the pump is like this, fluid going in here, coming out here. Any significant height difference or not? Here one, if you just consider before the pump and after the pump. Alright? Any height difference or not? Not much, huh? Yeah, very small lah. Head loss, well, there's no pipe here, so, alright? Because we're only considering before and after pump, no pipe, no minor losses and so on. It's just that if there are any losses, it's to do with the pump, not to do with any other thing. Alright, no turbine here. The velocity, any difference or not, going in and out of the pump? Some say can. Normally not much also, because m dot is equal to rho AV. Alright. So m dot 1 is equal to m dot 2. The pipe, have you seen a pump or not? Maybe I showed pump. Last time I showed. Okay. Pump. So images. Alright. You see much difference in the diameter in and out? It's the same, isn't it? Normally the same pipe one. Okay, flange fitting here. That for the yesterday you asked about flange. Okay, it looks about the same. Okay, so that same pipe going in, same pipe coming out, more or less. All right. Okay. So can I say V1 is approximately V2 because A1 is approximately A2. Therefore, is that all right? Okay or not? All right. So this one. Oh yeah. So if you just analyze the pump alone, the head is actually, what the pump does is put in flow energy. The pressure, right? The pressure will rise across the pump. The P2 will be higher than P1. And that's how the pump puts in the work into the system. Not through the other areas, not through head rise, not through elevation, not through velocity change. Right? So the head rise is through the difference in pressure. Okay? So coming back here, since we can, this head pump, all right, so we can either, for the 5 kilowatt rated pump, we can either increase, have a very high m dot, move a lot of fluid, and by the pressure difference is small across the pump, or we can move a little bit of fluid and have a big pressure rise across the pump. All right, so same argument, whether you want to talk in terms of head or in terms of pressure, because head is, in this for the pump, the head is just the pressure rise. Is that okay so far? Okay. All right. So we'll look at the different. So when it comes to pump selection, all right, you need to decide which situation you are, what you want to do, whether it's a high flow rate situation or a high head situation, and choose the pump accordingly. So let's look at the different type of pump. Okay. All right. So, no, I'll come back there. I see some nice pumps there. Okay. So, okay. So the pump, first type, which we don't use that much in this unit, but I just mentioned here, is a positive displacement type. So example is like this bicycle pump, sorry. You have a piston, all right? Each time you displace a fixed amount of gas, okay, and then drives it through the system. All right, this one's manual one, but you can have mechanical pumps. All right, and this one are normally for the high pressure, high head, low mass flow rate. All right, so positive displacement means each time it moves, it displaces a fixed amount of fluid. So by having a piston, you can actually push a very high, depending on your stroke of your piston, you can actually push generate a very high amount of pressure. All right, either in gas or in liquid. All right, so sometimes this one used in gas is normally called a compressor. All right, air-con compressor also works this way. It has a piston, all right, arrangement, except it's a bit more complicated, but generally there's a piston arrangement inside there. Your heart also works this way. As I say, each time your heart opens and shuts, it displaces a positive amount of fluid. Other example is like hydraulic equipment. If you hear the word power pack floating around, the power pack is basically a very high pressure pump inside. Okay. Other examples I saw just now here. Okay. It's like a gear pump. All right. So the gear pump, sometimes 2 gears, sometimes 1 gear, but it traps the fluid between the gear teeth and pushes it along. So each time there's a positive volume that's getting pushed along, every time the gear spins in here. All right. So gear pumps and so on. But as I said, we won't talk a lot about this in this unit. It's not so appropriate. Yeah, the pump. Your shoe also. All right. Okay. So. Okay so far? All right. So that's the first type. All right. Another example is this one, piston. All right. This one is an engine, so there's other things going on in it. But you don't have to have other things going on in it, like an air compressor. All right, they use for making compressed air in everywhere, workshop and factory and so on. It's actually normally a piston with a crank slider arrangement to pump the piston up and down. Valve opening and closing to make sure that you take in air, you compress it, then you open, and then it siphons to a pressurized tank or somewhere. Okay, so heart is a positive displacement pump, but if artificial one, normally no. Artificial one is a screw type pump. All right, not positive displacement. Okay, we'll talk about the not positive displacement one first. All right, heart got 4 chambers. You get blood go in one. That's a valve, and then okay, the valve allows the fluid to go in here. All right, when this one contracts, this valve will close, this valve will open, and then the high pressure goes out here. All right, so it sucks in here and goes out here. So there's two pumps in one, so there's actually 4 valves here. Right, one for the right side, one for the left side. This one drives blood through the rest of the body, and this one drives blood through the lungs, I think. Something like that, is it? I'm not very sure about piping. I don't do this type of piping. Okay? Alright. Then, on the other extreme, so this is the, alright, so where's my notes? Okay? Positive displacement. Is for m dot power is equal to m dot GH. It's for the high m dot. It's for it's for m dot low H high. All right. So that's the positive displacement pump. That's number 1. Number 2, I think normally axial flow. Okay. This is actually going to turbo machinery. Turbo machinery is anything that normally rotates and associated with fluid. We call it turbo machinery. Alright. So axial flow is the other extreme. M dot is high, the head is low. Okay. So although you can use the pumps in the different one, alright. You could possibly use the axial flow pump to do the first job and so on. You can mix and match, but the efficiency won't be there. All right. Because I told you this efficiency. You want this efficiency to be high normally. Okay. If you don't select the right pump for the right job, normally your efficiency will be severely compromised. So although it may work, but you may get very low efficiency. All right. So second one, axial flow. That's why we need to select the right pump. It's basically like a fan. There's the picture here. Okay. No. Okay. So it's basically like a fan. All right, in a duct. All right. So I don't know. There's no good picture. I go for picture. Fans. Okay, so they're like that. All right, use in ventilation. All right, applications and so on. You want to move a lot of air. In this case, air. You want to move a lot of air. Head rise don't need so much because the pressure inside here. What's the pressure inside here? Atmosphere. What's the pressure outside? So you don't need a lot of pressure difference, isn't it? Okay. So you want to move a lot of air without pressure. Don't need much pressure difference. All right. Just a slight, small amount of pressure difference so that it can drive the air. It can overcome any losses that it has. Okay. So it's used. This is the internal one. Okay. Different designs. External one also same. Like the propeller on aeroplane or helicopter. Also meant to move a lot of m dot with very little pressure difference. So what's the pressure difference before? Then in front of a propeller and behind the propeller is about the same. It's about more or less atmospheric. Okay, so it's meant to move a lot of m dot. Okay. Then the final one, centrifugal, is the m dot moderate and the h also moderate in between. Okay. So centrifugal, all right, axial because the flow moves axially to the pump. Centrifugal is what we saw just now. Go back here. All right, this one I think I talked about it earlier already. Okay, the flow goes down the middle tube. All right, it comes out the top tube. Got picture inside. Maybe if I put centrifugal, you get more. Okay. Yeah, picture like this. So this is the inside. The flow comes down the center here, comes axially in, spin, or spin this way, and it collected out on the body here and it thrown out. Alright? So how it works is, alright, when the fluid is spinning, alright, when you're spinning, you need something to hold you in, isn't it? If not, you'll be thrown out. Correct? Okay? So same here, when you spin the fluid, you need something to hold it in, but there's nothing holding it. Okay now? Alright, so the fluid, I'm spin, you realize, hang on, I want to go straight, so it will spiral outwards and get collected here. Alright? So that's how the principle of this pump works, by spinning the fluid. Then the fluid generates centrifugal force. There's nothing to hold the fluid back, so the fluid will then spin out. Okay? So this is a very common. We used it in all our labs. Alright? It was in the I was normally at the bottom of the rig. There were small ones, and you can get very big ones also. Alright? There's some very big ones in the service room behind here. I think it's there. Alright, but I think cannot go inside. Alright, and I think those doing mechanical, they did a design one. You went on a field trip. You saw these type pumps being built. Alright, they were casting it in Ipoh. Alright, so they're casting the body. Alright, then I guess they buy some motor from China and connect to it, is it? Alright, so they were casting the body and the impeller mainly. Is that correct? They were not making the motor. Alright, so there's normally these pumps very common. used in law application, buildings, pump the water up, and all that water applications and so on. Okay. Any questions or what so far? All right. So that's the different type of pump. Okay. And in pump selection, so I might as well talk about the selection now since I covered the. All right. We want to find one with the efficiency is high. So we need to look at the case. All right. Okay. So let me skip in front. No, here got picture of centrifugal pump. This is a rusty, lousy looking pump. This is the inside. Okay, where? Okay, this one. All right. So since I just waving my hands telling you this is for high flow rate, this for low flow rate, and so on, put some numbers to it so you know how to use and know how to select which pump. That's the number. This is the number here. We use a specific speed. All right. So the specific speed is defined as the flow rate coefficient. Remember the flow rate coefficient? Did a few weeks ago. All right. To the power of half divided by head coefficient to the power of 3/4. What's the dimension of flow rate coefficient? Huh? Dimensionless. Correct. Head coefficient? Dimensionless. So, what do you expect the specific speed dimension to be? So, actually this one, no matter what power you put up and what power you put down, it will be dimensionless. Okay? So, by this case, they just selected, possibly there was some thinking to the number, I'm not sure. Right? But they selected half to the CQ to the half, CH to the 3/4. But you put any number there also, it will be dimensionless. Alright, but anyway, this is, if you want to come up with your own convention, you can, but then you have to come up with your own graph. If you follow the standard graph, right, it's just arbitrarily chosen that way, then we chose CQ to the half, CH to the 3/4. Maybe there's some thinking there. Okay? Alright, so if you put that, CQ is that, CH is that, so we put that together and rearrange to get our omega Q to the half over GH to the 3/4. That is the number that we will use to determine whether which pump to choose from the graph that I'll show you later on. Right? Basically, in there, there's Q and there's H. Right? So it's a ratio of Q over H. Q is the flow rate, so either high m dot or H high head. Right? So high flow rate, this number will be big. High head, this number will be small. Right or not? Okay? High flow rate here. So high flow rate, this number big, you expect this number big. High head, this number big, you expect this number to be small. All right, that's the relationship. So a big NS is for high flow rate application, axial fan. Big H is for high head application. Small NS is for like compressor and all that, positive displacement. So I write it down. Okay, so NS is equal to, what is it? Omega Q to 1/3, Q to half, GH to the 3/4. Omega Q to the what? Half over G head pump to the 3/4. Is it correct? Okay, so for Q high, what's the Q high? We expect the NS to be high. Alright, so basically this one is axial flow. Alright, for Q low, for head pump high, we expect the NS to be low. Then maybe centrifugal or positive displacement. Alright, but our selection, positive displacement is actually a more specialized area. Our selection graph only covers axial flow and centrifugal. Alright, okay, so that's extension of the idea I just presented. Any questions? All right. So, pump here. All right, copy it here. I save it anyway. So, the US again. This one is in SI units. This one is in US modified dimensional form, so it actually has a dimension, but you know, okay. The textbook shows both graphs, but we normally just, if you don't use the SI unit one, normally adequate. Okay. This number is not one-dimensional. It has a dimension to it, right? So that one, it's a different system, different convention. All right. Okay, I've described that one. All right. So the graph here looks like this. Okay. So for high specific speed, high flow rate, there. This is your specific speed here at the bottom. After you put in the numbers for omega, Q, in the head, all right, you can calculate the specific speed. So for a particular application, you calculate the specific speed, then you find it. The number is 3.5. Say, then you look up here, all right. It's 3.5 here. The recommendation is go for axial flow pump, all right. High flow rate, flow head wise. Okay. But in other application, you calculated that number is maybe 0.3. Then you go down here. This radial flow pump is the centrifugal pump, right? So that's why this is a cross section of that centrifuge. It's spinning this way, the flow is going up. Right? Going in from the middle, right? So in between, there's a category called mixed flow, where it's partially axial, partially centrifugal. If you don't understand the picture, I'll show you here. I try to draw here, hopefully it doesn't crash. Okay, so axial flow, can draw? No, cannot draw. Alright, axial flow, the flow go like this. Yeah. Arrow. No. No, I need to enable everything first. Okay. So now try draw. Alright, axial flow, the flow go like this. Okay or not? Alright, this is the hub, this is the axis. Alright? But it goes, although it's spinning, alright? But it goes more or less axially like this. This one, the flow comes in and goes out like this. Alright or not? That's the centrifugal one. Comes into the center. Comes in the center, spin, and then it goes up. Alright? Next one, there's a little bit of both. Alright? Bit of axial flow, bit of spinning, and goes out like this. Okay? So that's how you read this picture in the middle. Okay? Any questions so far? So you all clear what axial flow pump is, a centrifugal flow pump is, and a positive displacement pump is? Right? So in this unit, we normally, most of the time, this one. Okay? This unit, we focus mainly on centrifugal pump. That's the most common mid-range, middle application one. Alright? Not so much on axial flow, and actually to this end here, the graph doesn't have. To this end here is positive displacement. Alright, that's even more extreme high head, low, even lower flow rate. So it's not in this graph. Alright. Normally that's not fluid mechanics. That's more thermodynamics, hydraulics, hydraulic machinery, and so on in this category. Okay, fluid power, all that kind of area. All right, so that's why in this fluid mechanics textbook they left it out. Okay, let me save this as well. Any questions so far? Okay, so Now, what we do, all right, normally for pump problem, we don't just look at the pump. We need to look at the system. But before I continue, any questions, sir? You okay, huh? What I discussed not too complicated, huh? All right. So let's say system. Okay. Got pipe coming here, go here. Pump symbol normally like this, huh? Okay. Normally they draw like this. Okay, with the pipe going in the center and the pipe coming out the end here. Something like that. Okay, that's symbol for centrifugal pump. And so on. Okay. So this is say 0.1, this is say 0.2. Okay. So in this case, I can bring this back in. Well, all right. So we can say P1 on rho G plus V1 squared on 2G plus H1 plus head pump is equal to P2 on rho G plus V2 squared on 2G plus H2 plus H loss plus H turbine. Okay, in this case, there might no turbine now. Alright, when you are pumping the fluid. The turbine case is normally when every power generation, like a hydroelectric plant, we're converting the flow energy to some mechanical energy. Alright, then we got turbine. So in a rare instances, you might have a turbine to actually take energy out. But in this case, let's say we don't have. So, what I'm going to do, like what I did earlier, I rearrange. H pump is equal to P2 minus P1 on rho G plus V2 minus V1 on rho G plus H2 minus H1 plus this head loss is F L on D plus sum of K V squared on 2G. Alright. So this one we normally call the system. This one we call the pump. Alright. Oh yeah, the square got missing. Okay, so far? You still agree about this? I didn't pull any fast one yet. Didn't trick you or anything. Alright? So, if you look at it, let's say for the example earlier, alright? Let's say for the example earlier, I sketched for now, but actually if you do the thing, you can actually plot P2 minus P1. In that case, maybe that one is constant, alright, or maybe even 0, alright. V2 minus V1, both of them are 10, so that one is also 0, alright. H2 minus H1, maybe that's a constant, okay. So at zero flow rate, so if I plot, this is the H versus, well, this is H system, this is H pump. So H versus, say, Q. Alright. So, at zero flow rate, this one is 0. That one. So, it starts off at some number here. Maybe that number is H2 minus H1. Okay? At Q equals 0 here. Alright? What happens when I increase the flow rate? Alright? Q, alright? Q equals to velocity times area. So, we assume the area is constant. So, Q is proportional to velocity. Alright? Okay? So if I increase the flow rate, I'm increasing V. What happens when I increase V? Well, P2 and P1 is not going to change. V2 and V1 is not going to change at the final and initial velocity. H2 minus H1 is not going to change. But in the head loss term, you see that V squared? That one will change. Right now. Right? So it will increase. Alright? Increase. Alright? This is called the system curve. Alright? This is equal to this whole thing here. Alright? And it increase like a, what's it called? Parabola. Parabolic. Alright? To the power square. Right? So, this H2 minus H1 plus that F L on D sum of K on D square 2 D7. Alright? It may not be exactly parabolic because F might vary with your might change slightly with Reynolds number. Okay? So it may not be exactly parabolic. But never mind. It looks something like this. May not be perfectly parabolic because F not constant. Right? F is a function of RE and E over D. Okay, and RE changes when you change velocity. Right? So there could be, may not be actually perfectly periodic, parabolic, but never mind. Alright? I just sketch for now. If you have for a particular problem, you can do that. Alright? If you got time. Alright, maybe you cannot sleep, you want to do. You can actually plot each data point here. Alright? What happens is Q here, here, and so on. So for each data point, you can find the flow rate, you can find the velocity. For each flow rate, you can find the velocity, can calculate random number, look up F, put it back inside here, and so on, and get back that number. Is that okay so far? Can be done. We'll do the tutorial. Alright. Okay? And next thing is the part. So where this equals that is the intersection point. So the pump curve, alright, the pump performance curve or pump curve, H at the function of flow rate, that you can either do experiments or get from the manufacturer, they will provide the data. Alright? Hey. Alright? So the pump curve will typically look something like this. This is the H pump. Alright? Some might ask why. Why? Why? Okay. Alright? But before I tell why, okay, so for the system to operate, alright, the system, this equals that, energy in equals energy used, and so on. Alright? In this particular system, the equilibrium point will be here. Alright? This is the operating point. Alright? When your head from the system is equal to the head of the pump. Alright? That equation up there is only valid at this particular point. Alright or not? Alright? Okay, I'll let you copy this before I go to the next page. Because then I'll explain why. Okay, you all happy? You have a question? Any questions? Alright. So why is because here, that's the pump. Alright. So if you okay, so the flow comes in here, spin, and goes out. Alright or not? Okay, take this one. Alright, spin, and go out. Okay, at high flow rates and low flow rate, okay, at no flow rate, let's say, start with no flow rate. You put a valve, you turn it off, and you let the pump spin. It gets hot now, but Alright, so don't do it too long. Might damage the seals and so on. Okay? So imagine you put a valve here and you shut it off and you still turn it on. Now the fluid is spinning around, alright, and not going out. So it will generate a lot of centrifugal force, isn't it? So you expect the pressure here to be a lot higher than the pressure here. Alright? And therefore, from the earlier one, if you have a big difference in pressure for across the pump, you have a big head. Alright now? Is that okay? So I repeat again, some still a bit puzzled. I close off the flow. The fluid is just spinning around, not flowing at all. Okay? It will generate a big difference in pressure because of the centrifugal force. Big difference in pressure between here, the inlet, and here, the outlet. Alright? And that one, therefore, you get a high head. Okay? That's the maximum your head are. Alright? Okay? So, if you let the fluid flow, then the fluid will no longer just go round and round. Alright? It will start to leak. Well, not leak, but it will start to spiral out. Okay? It will start to spiral out. Alright? So, in that case, it does not spend as much time spinning. Okay? Some of that centrifugal force that it would have developed, it would have used to move outwards. Okay? So the centrifugal force is now less. Right or not? Does that make sense? So if instead of just spinning around in the circle, it's spiraling out. Right? So since it is spiraling out, it is accelerating outwards. It is losing some of that pressure, some of that force to keep it in. Alright? So in that case, the pressure out here will be not as high as before compared to the pressure inside, because the fluid is no longer forced to move in a circle by spiraling outwards. So some of that force is lost. Alright? Maximum pressure difference will be if the fluid keeps moving in a circle. If the fluid is not moving in a circle but instead it's spiraling outwards, then the difference in pressure between here and the center will be less than the maximum. Right now. And when you have less pressure, then you have less head. Because the pressure is just this one. Alright? Less pressure, less head. So, that's why the graph looks like this. Here, the fluid is spinning in a circle, not moving anywhere except going around in circles. Here, the fluid is spiraling outwards, so you get less pressure developing. And over here, at the other extreme, the fluid spends no time spinning at all. It just goes straight from in, go to out. Then it develops no head at all. Quite not. Alright? So if you don't spend any time spinning, it just goes straight in, go around the, instead of doing any spiral at all, it just goes straight radially out. Then you expect no head to be formed. Alright? These are the extreme, no spinning. Maximum spin, no spin, and then in between, some spin and some radial movement. Okay? That's why the head curves like this. Alright, can be measured. Alright, so that is your system curve. Alright, at the intersection of those 2 points. Any questions? So normally, alright, we'll do other things later. A few other things I need to talk about. Pump in series, pump in parallel, and a few other things. But I'll just finish off with this one last concept. So for a particular system, it looks like this currently. But let's say you change something. Alright? You play around with the valve. Okay? Alright? So this is system original. Alright? So I pick color blue. Alright? So let's say itchy fingers, you play around with the valve. So when you play around with the valve, maybe your KL go up. Alright? Your minor losses go up because you didn't close it off completely, but you close it off a little bit. So this one go up. Alright? So in this case, the new curve will look something like this. It'll still start off here, but it will move up like this. Alright? So once the system reaches equilibrium after you put your itchy hands play with the valve, right? The new flow rate will be lower, lah, obviously, right? And that's all here. Right? So that is Q goes down because KL go up, say. Okay? So again, this is the first original equilibrium point. This is the second equilibrium point. After turning the valve, so expect your flow rate to go down. That's how a valve controls the flow rate. Alright? So you still have the pump there driving the system. Alright? Okay? I have the same example since I talked about it yesterday. Alright? If this, but your heart not centrifugal pump, but some sort of pump. Alright? Also maybe has some sort of pump curve. This is called pump curve. Alright? The rest of you, alright, all your arteries, veins, and so on, and all the organs that the blood supplies to, has the curve like this. Alright? So your flow rate, for typical pumping rate and so on, blood flow and measure like this. Alright? So after, in that case, there's no valve to turn off. But let's say, alright, you write in red because that's blood. Alright? So after many years of partying and cigarettes and alcohol and other things, alright, what happens is possibly your diameter go down and your friction factor go up. Alright? The healthy artery has a nice soft slimy wall one. Alright? The unhealthy arteries, the plug gets in, it forms a layer, and then after a while that layer hardens. Alright, and that's why and then it hardens, and that it not only narrows the passage but also causes a lot of friction on the wall surface. Okay, so these two things happen, and you also get possibly this one. Okay, so you get reduced flow rate. So this is a young healthy woman. After many years of good life, it gets here and here and here. Alright, so your flow rate goes down and down and down. Alright. And then at some point the flow rate is below what is needed to sustain your other systems, and therefore you get a stroke, and so on. If you catch the situation before you get a stroke and die, sometimes you get a stroke and survive, but alright, then what you do is you have a bypass. Green. With bypass. Alright, that's where your parallel pipe comes in. Alright, with bypass, then you have another pathway. Then maybe your curve hopefully may not go all the way back here, may go down again. Alright. All those parts that are badly clogged up, alright, you have a parallel pipe there to reduce the then from the red intersect here to your new curve after the bypass, after the grafting and all that, open heart surgery, staple it back close. They basically have a saw that open the rib cage down the middle. Play around with the part inside. Close it back. Let's staple it. Either normally tie or staple it back. Okay? So try to avoid that. Then you get your hopefully flow rate is good again. Don't get stroke. Alright. So I'll stop there. We'll do tubes on pipe flow, not pump this week. Next week. Oh, I forgot to mention, I sent out an email yesterday. This Thursday, right, I hope to return I have about 8 more to mark, your flow measurement prac by this Thursday. And also I want to talk about the pipe flow prac. So the lecture from 5 to 6 as normal. And then I talk about the pipe flow prac, what you need to do and blah 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 at 6 o'clock. So expect to finish at around 6:30, give or take, plus minus 10 minutes. Alright, depend how we go. Alright.